Greetings, students. You scoundrel! What are you doing here? Do you expect me to listen to you? No, Mr. Bond. I expect you to learn about hybrid orbitals. The subject of today's lecture is valence bond theory. And we're going to cover the whole spectra of topics on it. What is valence bond theory? Valence bond theory is a quantum mechanical model. The words are evil. Valence bond theory is a quantum mechanical model that shows how electron pairs, and suddenly I'm British, that shows how electron pairs are shared in a covalent bond. So according to valence bond theory, how does a bond form? The simplest way we can look at it is to simply look at hydrogen. We have two atoms of hydrogen. These two atoms of hydrogen have only one orbital to them. Why do they have only one orbital to them? Because they're hydrogen. And since they're hydrogen, they can have only one orbital. So we have our one atom of... Just a second. Alright, so we're hydrogen, we have one orbital. And in our one orbital, we have one electron. I see another hydrogen orbital, and I want to bond with it. How do I bond with it? Usually I divide an evil trap and lure Mr. Bond into it. And then I talk him to death until he escapes. Which is very rude, because he should have been listening to me. It's only manners, after all. But at any rate, I digress. If these two hydrogen atoms are to bond, they have to have electrons of opposite spins. Why must the electrons be opposite spins if they're to form a bond? Well, what's a bond? It's a shared pair of electrons. Two electrons that are going to occupy the same orbital. And according to Pauli, if two electrons are going to occupy the same orbital, they have to have opposite spins. So if we're going to form a bond or a shared pair of electrons, and these shared pair of electrons are going to occupy the same orbital, then they've got to have opposite spins. So my two hydrogen atoms move close to each other. They have opposite spins. The two atoms are going to move closer and closer and closer together until the two orbitals overlap. The two orbitals overlap, and what happens? These two electrons can now move to either atom. I like to think of it not as a physical overlap, but I like to think of it as these two nuclei have gotten so close together that in a statistical model, the probability of this electron belonging to this hydrogen atom is equal to the probability of it belonging to this hydrogen atom. And this electron's probability is equal to that. So what we have, when we have a bond form, is we have the bond formed by an overlap of orbitals. Unfortunately, neither orbital is being destroyed. It would be nice if these two things were scrunching together and there was a big, great ball of evil destruction. But unfortunately, that's not what happens. Instead, they decide to do the nice goody thing, and they each get to keep, and they each keep, and they each get to keep their own orbital. After all, when we look at our molecule here, do we see a destruction? Do we see a destruction? Have either of these orbitals been destroyed? No, they simply overlap. And these two electrons are shared between the atoms. They can belong to either atom. So, according to valence bond theory, so, in valence bond theory, each atom keeps its own orbital, and the electrons move between the two atoms. Now, hydrogen's the simple case study. Let's take a look at fluorine. I once tried to destroy a secret agent. He was a platypus, by boiling him in hydrofluoric acid, but that's a story for another day. Right now, we're not going to form hydrofluoric acid. We're simply going to form a molecule of diatomic fluorine. Diatomic fluorine forms, according to valence bond theory, when the two orbitals of the fluorine atom overlap. Now, the fluorine atom has all its orbitals filled except for its last p orbital. Therefore, if it's going to form a bond, it's going to have to be because of the overlap of those empty p orbitals. Now, p's aren't nice spheres. Our s orbitals were spheres. Our p orbitals are ice cream cone shaped. And you'll remember I briefly mentioned that these ice cream cone shapes have different phases. And these phases are technically caused by constructive and deconstructive interference of the electron wave. But now these two phases aren't simpatico, meaning they can't overlap. If there's going to be an overlap, it must be of the portion of each orbital that is of the same phase. In other words, red has to overlap with red, and blue would have to overlap with blue. So here, for our fluorine-fluorine bond, we're bringing the red ends, or the red phase, of two p orbitals together. Just like before, in order to form this bond, they have to have electrons of opposite spins. So we've added an additional condition. First, we had to have electrons of opposite spins in our orbital, and now the orbitals have to have the same phase. The overlap must occur between between the orbital parts of the same phase. Now, we are ready to give name to our creation. We are ready to name the monstrosity. We are ready to talk about what it is that we have created, what it is we have wrought. And we name it sigma bond. Whenever there is an overlap of orbitals, head to head, it is referred as sigma to a sigma bond. It should be noted that even though they give you the sigma bond down here, that not only is that a sigma bond, but that is a sigma bond as well. Whenever two orbitals can overlap head to head, that head to head overlap is referred to as a sigma bonds. Single bonds are sigma bonds. In other words, that first bond to form between two atoms is always the head-to-head overlap, or the sigma bond. Now, this is very important information if you're to confront the man with the golden gun. Everybody write down the man with the golden gun. Write down the man with the golden gun. To summarize what we've talked about on the previous slides, valence bond theory is a quantum mechanical model that shows how electron pairs are shared in a covalent bond. A covalent bond forms by the overlap of atomic orbitals. In order for this overlap to occur, two things have to occur. Each one has to contain an electron of opposite spin. Second thing, the two overlapping lobes must be of the same phase. Each bonded atom maintains its own atomic orbitals. Again, no glorious destruction. Where can an evil genius find solace in quantum mechanics? But the pair of electrons, even worse, are shared in the overlapping orbitals shared by both atoms. The greater the amount of the overlap, the stronger the bond. In other words, the more interests they have in common, the stronger the bond. Another way of thinking about it, two nuclei are brought so close together that the two electrons have an equal probability of belonging to either nucleus, or have a significant probability, rather, of belonging to either nucleus. I don't want to say equal, because that would be evil. All right, now we want to explain what appears to be a simple molecule, but in reality is actually quite puzzling. I have methane. Methane, if we look at its Lewis structure, is carbon forming single bonds with 4 hydrogen atoms. You're saying, okay, carbon can form 4 bonds. What's wrong with that? Well, here's what's wrong with it. Look at the electron configuration of methane. Look at the electron configuration of carbon. If we look at the electron configuration of carbon, carbon is helium 2s2 2p 2. Think about what we just talked about when it comes to valence bond theory. For each one of these single bonds we have up here, in order for them to form, carbon has to have a single electron in an orbital. For every single bond carbon forms, it has to have an electron that contains only one, an orbital that contains only one electron. If we look at its electron configuration, how many orbitals containing only one electron does carbon have? Carbon only has 2 electrons with a single electron in it. So in theory, according to valence bond theory, carbon should only be able to form 2 single bonds because it only has 2 orbitals capable of overlap. So how in the world is it forming 4 bonds? We know carbon forms 4 bonds. Say that 10 times fast. Stop laughing at me. I said stop laughing at me. You're still laughing at me. Stop it. Stop it. Stop it. It's rude. But at any rate, we know this compound exists, and we know it exists with 4 single bonds formed. So how can we explain this? Well, could helium be donating? Could hydrogen here be donating 2 electrons to form a bond in this empty orbital? No, it can't, because our hydrogens each only have 1 electron. So what in the world is going on? When confronted with a puzzle like this, what is a chemist going to do? Make something up! We're going to make up a new theory, right? And our new theory is orbital hybridization. What carbon does is carbon says, I have 4 valence electrons. I need to gain 4 more. In order to gain 4 more, I'm going to need 4 orbitals of equal energy. Well, if carbon took its 4 electrons in its valence shell and distributed them between each of its 4 valence orbitals, it would have 1 electron in each orbital. So you're saying, well, that must be what happens, right, Dr. Kelly? Bzz, wrong. Kind of. Here's the problem. And here's why we know this doesn't happen. If this were to happen, are we really forming 4 bonds that are equal? No. Here's why. Remember, the 2s orbital has less energy than the 2p orbitals. So we would be forming 4 bonds with carbon if this happened, but one of these bonds would be significantly less energy than the other. And when we examine methane, we know that all 4 bonds are of equal energy. So that can't quite tell the story. Well, what if instead of what if instead of just distributing electrons, distributing its valence electrons equally, it distributed the energy of the valence shell equally? Ah, now we're on to something. So what carbon does is carbon says, okay, I have 3 orbitals. I'm sorry, what carbon does is it says I have 3 orbitals of high energy and 1 orbital of lower energy. I'm going to take these 3 orbitals and I'm going to merge them together and average out their energies and come up with 4 orbitals of equal energy. Now I need a good name for these 4 orbitals I formed of equal energy. Well, I made them from an s orbital and 3 p orbitals, so why don't I call them sp3 hybrid orbitals. And what's a hybrid, right? A hybrid is an organism that results from the mating of parents of 2 different species, right? If you mated a Chihuahua with a German Shepherd, their offspring, in addition to being absolutely hideous and bizarre, would be a hybrid, right? That's what we're doing with our orbitals. We're mating our s orbital with our 3p orbitals and getting 4 new orbitals of equal energy. And we call these 3 new orbitals sp3 hybrid orbitals. So now we have 4 orbitals of equal energy. We can place 1 electron in each one of these 4 orbitals of equal energy, and that would allow carbon to form 4 bonds of equal energy. This concept is known as orbital hybridization. I don't know why they put that there. I don't want it. It's just a little bit more neatly than my chicken scratch shows you what occurs. When carbon bonds, it takes its 4 valence electrons, it distributes them between its 4 valence orbitals. There are the 4 valence orbitals. is taken those 4 valence electrons and it's placed 1 electron in each one of its 4 orbitals. Then it's hybridized the energy of the 4 orbitals to form 4 new orbitals, all of equal energy. We refer to these new orbitals as sp3 hybridized orbitals, or sp3 hybrid orbitals. Why? Because we used 1 s orbital and 3 p orbitals to make it up. Now, one of the things that's neat about orbital hybridization is that you're adding an s orbital, that's a sphere, s orbital is a sphere, and you're adding it to a p orbital, or a series of p orbitals, and these p orbitals are all two-lobed, right? They all have 2 lobes. Well, you're not just averaging energy, you're also averaging their shape. So instead of winding up with these shapes, you wind up with 4 orbitals, all of which have a big lobe, and I can't draw, and then they have a teeny tiny lobe over here, right? A big lobe and a teeny tiny lobe. So that's your new shape. This new shape, fortunately for us, when we begin to talk about molecular structure, is really familiar to us. This new shape is pretty much the same shape as a balloon, where you have one really big orbital and a teeny tiny part of that orbital. So your sp3 hybrid orbitals all have this balloon shape or balloon quality to them. However, you don't have to look at my high-tech graphics here. You can instead look at some professionally computer-generated graphics if you want to. I mean, just if you want to here. If we look at these high-tech, fancy computerized graphics, we can see our carbon with its... Whoops, that color's not going to show up there, is it? You can see our carbon with its sp3 orbitals, each containing 1 electron. We now have orbitals containing 1 electron that can overlap with the hydrogen 1s orbital. So we have a bond formed between 1 sp3 orbital and the hydrogen, resulting in the formation of methane. Hey, it's just natural gas. And there's nothing more natural than... I can't even stretch it. Just write down GoldenEye. Just write down GoldenEye. Everybody write down GoldenEye. Everybody write down GoldenEye. All right. This shows you a much better view of what I was talking about when I was talking about the shape. You have oh, that's not going to work. Just a second. You have a s orbital, and then you have your p orbitals. And your p orbitals are not only dumbbell shaped, but those dumbbells have opposite phases. When we average the energy of these, what we wind up with is again, a 2-orbital shape, but instead of the orbitals being equal size like they were in the p's, we have one orbital that's much larger than the other. When we view all these orbitals clustered around our atom, in this case our carbon, carbon's right in there, they form a shape known as a tetrahedral. These sp3 orbitals form a shape that looks like a tetrahedral. Fun fact, if you go to the store and you blow up 4 balloons of equal size, those 4 balloons of equal size will automatically form a tetrahedral. A tetrahedral is a shape that looks like that. Kind of looks like a bacteriophage. If you've ever seen the little pictures where you've got the little ball up here at the top, and it's got this thin neck, and it's got the 3 little legs sticking down, that's what your tetrahedral looks like. Line up here, then 3 little legs going down at an angle. The angle between these legs here is 109.5. And this shape is referred to as a tetrahedral, and that's what everybody on the face of the planet calls it, except your author of your book, in case you're reading it, for some reason, completely at random, that makes no sense to me, suddenly begins dropping the term tetrahedron. Well, it's a correct geometric term. It's not something I've ever heard used by a chemist before. I've always heard the term tetrahedral. Used by a chemist to describe this shape that we're seeing here. You need to know that when you have sp3, matter of fact, let me write that down. Have sp3 hybridization of an atom's orbitals it forms a tetrahedral shape. When you have sp3 hybridization of an atom's orbitals, it forms a tetrahedral shape. The angles of a tetrahedral are 109.5, and you're responsible for knowing that as well. What do I mean by angle? Right there, right? 109.5. All right, let's keep chugging along. Okay, how can we explain double bonding using hybrid orbitals? Let's take a look at a really simple molecule here. Let's take a look at the molecule of ethane. In ethane, you have a carbon singly bonded to two hydrogens, forming a double bond with another carbon also singly bonded to two hydrogens. Now we have a conundrum, because we have three single bonds in here. I'm talking about one carbon. For each carbon we have three single bonds. And then we have one double bond. Our single bonds should be of the same energy. How about our double bond? Well, our double bond is going to have a different energy from those single bonds. So we have to come up with a scenario where we have three bonds of equal energy and one bond of a different energy. So if we were to look at our carbon here, what we're going to do is we're still going to form hybrids. Why do we still have to form hybrids if we've got one orbital that has to be of a different energy? After all, isn't that s of a single different energy to begin with? Here's the reason we have to form that hybrid still. Remember, carbon in its ground unhybridized state has two electrons in that 2s. So if we're going to get one of those electrons out of that s and into that p, we've got to do something to make that jump energetically favorable. That means that because we're taking one of its electrons, S demands to be taken care of, right? S is the person who only lets you borrow their lawnmower if you promise to take them out to dinner later in the week, right? So S is only going to give up its electron if it gets to play in its hybridization. So if we're needing to form three orbitals of equal energy, we're going to have to take our s and combine it with 2 of our p orbitals. So we're going to wind up with a situation where we have carbon with 1, 2, 3 sp2 orbitals, and then 1 p orbital that got to keep all its energy and its electron. So we've got 3 orbitals of equal energy here, and 1 with a slightly different energy over here. These sp2 orbitals are going to form a Y. That's right, they're going to go out and join the YMCA. They're going to join, and they're going to form what looks like the letter Y. They're going to form a kind of a divining rod. All those orbitals, those sp2 hybrid orbitals, are going to have that big lobe, little lobe shape that we saw for the sp3 hybridization. However, because there's only 3 of those shapes, all 3 of those shapes are going to lie in the same plane. These 3 shapes are going to arrange themselves in what's known as a trigonal planar arrangement. Not only are they going to arrange themselves in a trigonal planar arrangement, but because they're all in the same plane, what we're essentially doing is we're dividing a circle up into 3 equal parts, except I didn't draw very equal Alright. So much for my freehand skills. We're dividing a circle up into 3 equal parts, so that means each part would be 120 degrees. So each one of these parts is going to be 120 degrees off of each other. So I formed 3 orbitals of equal energy that have arranged themselves in a plane, trigonal planar shape, 120 degrees apart. And I have 3 orbitals now capable of forming single bonds. If we look at our high-tech graphic here, no, moving the wrong object. Stop it. Nope, stop it again. There we go. If we look at our high-tech graphic over here, we see our sp2 hybrid orbitals. Those are our green orbitals here. Our sp2 orbitals are 3 orbitals of equal energy capable of forming single bonds. And because we're dealing with our molecule here, we're going to form a carbon-carbon single bond by overlapping the sp2 orbitals of each of our carbons. So each of our carbon overlaps its sp2 orbitals. So how about the double bond? Well, remember, we said that we have a p orbital Remember, we said that we have a p orbital here that's of a different energy. So it's not lying along the same, it has a different shape than the others, and it lies along a different plane than the others. If we look in our picture, we see our traditional p orbital. These traditional p orbitals found in both of our carbons are going to overlap. The orbital is going to overlap in the red phase, and it's going to overlap in the blue phase here. It's going to form basically the double bond above the single bond and below the single bond. If you think about it, your single bond, or your sigma bond, is your pi filling. Oh no, Mr. Bill, that kind of looks like Mr. Blair. That's your pi filling. And this double bond here makes a pie crust because it's running above and below. And because it looks like a pie crust, we name this overlap of those p orbitals that runs above and below the single bond, we name it a pi bond. A pi bond is formed by a sideways overlap of p orbitals. Sigma bonds are formed by that head-to-head overlap. Sigma, head to head. They bump into each other. Our pi's have to do it sideways. So that's another type of hybridization. And yes, you're responsible for knowing sp3 sp2 hybrid orbitals arrange themselves in a trigonal planar shape at angles of 120 degrees. To each other. This is just a close-up view of what we were just talking about. You've got your two orbitals here that you're hybridizing with your s. They merge together to form sp2 hybrid orbitals that have that balloon shape. These balloon-shaped orbitals all lie in the same plane at 120 degrees to each other. Then this unhybridized p is there, and it's at 90 degrees to those other balloons. All right, we've got one last type of hybridization that we want to talk about, and it's one you just have to live and let die. Why don't you write down live and let die? I hope everybody's writing down live and let die. One thing you never want to live and let die, however, is a triple bond. And we can see triple bonds between carbon and carbon in something like ethine, or we could even see it in the cyanide ion. However, what type of hybridization gives rise to a triple bond for carbon here? Well, if we look at carbon here in ethine, it's forming two single bonds. Here's one single bond, here's the other single bond. So if it's going to form two single bonds, it needs two orbitals of equal energy with one electron in them. Also, it's forming two pi bonds. For those sigma bonds, it needs two orbitals of equal energy with one electron. For those two pi bonds, it needs two electrons. It needs two orbitals with one electron. So, once again, we need to take carbon's valence shell and distribute those four electrons between the four orbitals. Now, this time, we're only needing two orbitals of equal energy to form our sigma bonds. We also need to remove one electron from the s. We remember, s isn't generous. S isn't going to give up that extra electron unless it gets something out of it. So in order to get something out of it, it's going to require a hybridization. So, is going to merge one of the s orbitals with one of the p orbitals to form an sp hybridization. It's going to have two sp hybrid orbitals, and then it's going to leave two of the p orbitals untouched. So you have two hybrid sp orbitals, and then you have two p orbitals that haven't been hybridized. So these sp hybrid orbitals are going to be formed once again by combining a sphere with a double-sided ice cream cone shape. So once again, you're going to get those balloon shapes. If we look at it in terms of the fancy artwork, we get two sp orbitals from our two orbitals. We hybridize two orbitals, so we get two orbitals out. So we get those two hybrid orbitals that are balloon-shaped here, each one containing one electron. The farthest we can get two orbitals away from each other in three-dimensional space is 180 degrees. This 180-degree arrangement, where our orbitals are essentially opposite each other, is referred to as linear. So we would say our sp hybrid orbitals are arranged in a linear fashion. Then we have those two sp orbitals that are 180 degrees from each other. We then have our p orbitals that are 90 degrees off that hybridization. And that's going to produce a molecular shape for ethane that looks like this. So we've got my carbon over here forming a triple bond with another carbon that's forming a single bond with a hydrogen. So if we look at this carbon right here, it's got that sp hybrid orbital that's going to overlap with my hydrogen to form a sigma bond. So we've got our sigma bond forming right there. Then this carbon is going to overlap with this carbon by overlapping sp orbitals. And that overlap is forming a sigma bond, or the single bond. Remember, our double bonds are going to form from the sideways overlap of the unhybridized p's. I know I'm repeating myself here, but one of the bad things about teaching this way is I can't look at your faces and know if you're following me and saying, man, I wish you'd get on with it, or if you're looking at me and saying, we are totally lost and haven't decided the whole thing, and that leads to me repeating myself a little bit. So let me repeat myself. A double and triple bond forms from the sideways overlap of the unhybridized p orbitals. So we go back to our photo over here, and we're going to form a double bond by having that p orbital form this p orbital, the up-down p orbital, and this carbon and that carbon overlapping sideways and forming a pi bond. Our triple bond is going to form by the sideways overlap of this p and that p, right? So those guys are overlapping sideways to form our other pi bond, and our sigma bond's right there in the center. So our sp hybridization orbitals form our sigma bond, and our p orbitals form our pi bond. And you can see that over here in the book's fancy picture. The sps overlapping, then the p up and down overlapping, and then the sideway p's overlapping. Chemistry is easy, life is hard, yes? this is a really important chart. The only thing I would add to this is I would go ahead and, if I were you, I'd write down the bond angles to this chart as well. I would say that linear, we have a base bond angle of 180. I would say for trigonal planar, we have a base bond angle of 120. For our tetrahedral, we have a base bond angle of 109.5 on your AM dial. Oh, that would be an FM frequency. On your FM dial. So, you're responsible for knowing all this. And we're going to look at this again in the context of molecular shapes, because these hybridization, these hybrid orbitals, and how these hybrid orbitals are arranged around the carbon and around your central atom are going to lead to molecular shape. As a parting shot today, why don't you write down Dr. No? Write down Dr. No. That's right, the one that started it all. Dr. No. Beep. Oh, by the way, Dr. No is N-O. Beep.